The summer of 1950 found Enrico Fermi at Los Alamos National Laboratory in New Mexico, a place still humming with the energy of the atomic age. He was there to work, but also to reconnect with old colleagues from the Manhattan Project. One day, he joined 3 fellow physicists for a walk toward Fuller Lodge, where they planned to have lunch together. His companions that day were Edward Teller, Emil Konopinski, and Herbert York, all distinguished scientists in their own right. As they strolled toward the lodge, the conversation turned to something lighthearted. There had been a wave of reported UFO sightings in the news lately, and someone mentioned a cartoon from the New Yorker magazine. It showed cheerful flying saucers zipping away with trash cans poking fun at the whole flying saucer craze. The men laughed and talked about whether faster than light travel was even theoretically possible. It was the kind of casual speculation that physicists enjoyed, nothing too serious. But then something shifted. They arrived at Fuller Lodge and sat down to eat. The conversation meandered to other topics, the UFO discussion seemingly forgotten. And then, seemingly out of nowhere, Fermi spoke up. His question was simple, almost abrupt. "Where is everybody?" The table erupted in laughter, not because the question was funny in itself, but because everyone present understood instantly what Fermi meant. He was not asking about their lunch companions or the people in the dining hall. He was asking about extraterrestrials in that moment. The joke about flying saucers had sparked something deeper in Fermi's remarkable mind. If intelligent life is common in the universe, if civilizations rise and spread across the stars, then why have we seen no evidence of them? Where is everybody? It was classic Fermi, the same man who liked to ask his students how many atoms from Caesar's last breath they inhaled with each lungful of air, a simple question that revealed something profound. Enrico Fermi was the kind of thinker who could look at an impossible question and see a pathway to an answer. Born in Rome in 901. He established himself as one of the most brilliant physicists of the 20th century. His work spanned from theoretical predictions about ghostly particles called neutrinos to the practical engineering of nuclear reactions. In 1938, he received the Nobel Prize in Physics for his discoveries in nuclear science, specifically for his work with neutron irradiation and the creation of new radioactive elements. The honor came at a pivotal moment in his life and in world history. That same year, Fermi and his wife Laura left fascist Italy for the United States, where he would make his most dramatic contribution to science. In December 1942, beneath the stands of an old football stadium at the University of Chicago, Fermi led a team that achieved something humanity had never accomplished before. They created the first controlled, self-sustaining nuclear chain reaction. The apparatus, called Chicago Pile 1, was essentially a carefully arranged stack of graphite bricks and uranium. Fermi directed the experiment with characteristic calm and precision, calculating every variable in his head. When the reaction sustained itself, the atomic age had officially begun. This success led directly to Fermi's role as assistant director at Los Alamos during the Manhattan Project, where he became known as a kind of oracle for younger scientists. They called him the Pope because his judgments on physics questions seemed infallible. What made Fermi distinctive was not just his knowledge, but his method. He loved what came to be called Fermi questions, problems that seemed impossible to solve with available information. He would ask things like how many piano tuners exist in Chicago, or how many atoms from Caesar's last breath you inhale with each lungful of air. The point was not to get an exact answer, but to demonstrate that rough estimates could be built from reasonable assumptions. Step by step, you arrive at a number that is surprisingly close to the truth. This style of thinking, breaking down vast unknowns into manageable pieces, was exactly the approach Fermi would bring to the question of extraterrestrial life. Fermi did not just ask a question, he did what came naturally to him. He ran the numbers. Consider the scale of our galaxy. The Milky Way contains somewhere between 100 billion and 400 billion stars. Among those billions are similar to our Sun in size, temperature, and brightness. And here is the crucial point. Many of these stars are far older than our own Sun, some by billions of years. Fermi worked through a chain of probabilities. Start with the fraction of stars that have planets. Then consider how many of those planets sit in the habitable zone, that sweet spot where liquid water can exist. Add the probability that life emerges on a suitable world. Then factor in the odds that life evolves intelligence. Finally, estimate how long a technological civilization might last at each step. Even if you assign conservative numbers, something strange happens. The math keeps pointing toward a galaxy that should be teeming with intelligent life, given the age of many sun-like stars. Some civilizations would have had a massive head start on us. We are the newcomers arriving billions of years late to the party. Here is where the reasoning becomes unsettling, even with relatively slow interstellar travel. A determined civilization could spread across the entire Milky Way in just a few million years. That sounds like a long time, but compared to the age of the galaxy, it is barely a blink. If any ancient civilization had chosen to expand, their presence should be obvious. By now, we should see their probes, their signals, perhaps even their ruins. The calculations led to a conclusion that seemed inescapable. Earth should have been visited many times over, yet when Fermi looked around, he saw nothing but silence. The numbers said we should not be alone, the evidence said otherwise, and that contradiction became the heart of the paradox that still haunts us today. Here is where the paradox tightens its grip. If a single civilization developed interstellar travel and began expanding outward, colonizing nearby star systems, the mathematics of that expansion becomes difficult to ignore. Even moving at relatively modest speeds, perhaps 1% of the speed of light, a civilization could spread across the entire Milky Way in roughly 50 to 100 million years. That sounds like an eternity to us, but geologically speaking, it is a blink of an eye. Now consider the age of our galaxy. Many stars similar to our Sun are billions of years older. Their planets would have had a massive head start if intelligent life arose on any of those ancient worlds, and if that life developed the technology and the ambition to travel between stars, then their expansion waves should have reached Earth long before humans ever appeared. We are talking about civilizations that could have completed their galactic expansion dozens of times over by now. This is the colonization timeline problem. The math suggests we should be surrounded by evidence. We might expect to see the ruins of ancient colonies on nearby worlds, or detect the electromagnetic chatter of a galaxy teeming with intelligence, or perhaps we should have been visited so many times that the question would never need asking in the first place. Yet here, we are looking at a silent sky. The contradiction is stark. The time was available, the opportunity existed, so why do we find ourselves apparently alone? We tend to remember history as a series of lightning strikes. A brilliant mind suddenly sees something nobody else noticed, and everything changes. But the reality is usually more complicated. The question that made Fermi famous at that lunch table in 1950 had actually been echoing through centuries of human thought, waiting for the right moment to crystallize long before Fermi posed his famous question. A French writer named Bernard Le Bouvier de Fontenelle published a remarkable book in 1686 called Conversations on the Plurality of Worlds. It was an unlikely bestseller, a work of popular science that imagined a philosopher explaining the cosmos to a curious Marchioness. As they strolled through her garden at night, Fontenelle speculated that other worlds might harbor intelligent beings, and he wondered why we had no contact with them. The question was there, hiding in plain sight, wrapped in elegant prose and witty dialogue nearly 2 centuries later. Jules Verne touched on similar territory in 1865. The same year he published From the Earth to the Moon. Verne's writings reflected on the strange silence of a universe that seemed so full of possibility. He was a storyteller, not a scientist, but his imagination circled the same void that would later trap Fermi's thoughts. Perhaps the most striking precursor came from Konstantin Tsiolkovsky, the visionary Soviet rocket scientist who spent his life dreaming of spaceflight. In 1933, Tsiolkovsky wrote explicitly about the apparent absence of extraterrestrial civilizations. Despite the vastness of the cosmos, he framed it as a mystery that demanded an answer. This was 17 years before Fermi's lunch conversation. Yet Tsiolkovsky's words never reached the Western scientific establishment in the way Fermi's casual question would. The difference was not in the insight itself, but in the moment Fermi asked his question. At Los Alamos, surrounded by physicists who had just unlocked the power of the atom, the world was changing. And suddenly, the silence between stars felt less like philosophy and more like a problem that science needed to solve. Fermi gave the paradox his name, not because he was the first to see it, but because he asked it at exactly the right time in exactly the right room with exactly the right people listening. The paradox bears Fermi's name. But here is something curious: Fermi himself never wrote a single word about it. He never published his calculations or his reasoning. That famous lunch conversation in 1950 was just that, a conversation. 4 years later, in 1954, Fermi died of cancer. He took whatever deeper thoughts he had about the question with him for more than a decade after Fermi's death. The question lingered in oral tradition among physicists, but never appeared in print. Then in 1963, a young astronomer named Carl Sagan published a paper that brought the concept into the scientific literature. For the first time, Sagan recognized that this seemingly simple question pointed to a genuine tension between probability and observation. But there is another twist: the specific argument about galactic colonization. The reasoning that says advanced civilizations should have spread across the Milky Way by now is often attributed to Fermi himself. In reality, Fermi never made that argument during his lifetime. That line of reasoning was actually published more than 25 years after the lunch conversation by an astronomer named Michael Hart. In 1980, the cosmologist Frank Tipler expanded on Hart's work, developing the colonization argument into the sharp logical challenge we recognize today. So the Fermi paradox is not really Fermi's paradox. At least not entirely. It is a layered idea that grew over decades. Fermi asked the question. Sagan gave it form in print. Hart and Tipler built the logical structure around it. The name stuck because that original question, so simple and so devastating, came from a physicist famous for cutting through complexity with a few well-chosen words.